All right, back to business here. So solving log equations. So this is a good one to look at because it's really similar to questions where we solve trig equations and things like that too, right? So first of all, this looks dang near impossible right now because we've got x's inside of log functions and I've got two separate terms with x's. So what could I do here? See the dilemma there? How am I going to do that if I've got two separate terms? I mean, because to solve, we're supposed to isolate x somehow, right? What do you think? Becca's got an idea. Yeah, there you go. We have to use properties of logs to compress this into a single log expression, right? Okay, so we could do, whoops, we could do what then? How am I going to turn that into a single log expression? Log of A plus log of B is equal to what? Log of A times B, exactly. Yeah, log of product, right. So we could turn this into the log of x times x minus 3. Okay, now that's better, right? What's the implied base there? 10. So everybody take a second and write that as an exponential instead. If I transform that, and I could do it two ways. I could either do a base 10 exponential of both sides to cancel the log, or I could just, just think a log is an exponent. Okay, either way, what am I going to get with that? What's that going to turn into? A log is an exponent. So what's the exponent here? 1, right? And the base is, we already know the base is 10. So then what's equal to 10 to the 1? X times x minus 3. Now that's not so bad, right? That's starting to look like algebra 2 stuff, right? If I distribute the x, I get x squared minus 3x. If I subtract the 10 to that side, I've just got a quadratic function in quadratic equation in standard form. How would I solve that? Factor, yeah, this one factors, doesn't it? What are my magic numbers here? So if I solve, I get either x equals 5 or x equals negative 2. Okay. I should check those though, probably, right? Okay. Let's see, do they work? Now, think about your definition of a log function, right? Log functions, what's the domain of a log function? Okay, but not even 0, right? We can only input positive values into a log function. They're only defined for positive values. So if any of these are causing me to input negative values, then I'd have to discard them. Well, negative 2 is not going to work, is it? Actually, yeah, it is. Huh. It is going to work. Huh. Because if I plug negative 2 in, I'm going to get negative 2 times negative 5 is positive 10, and it works. Okay. True. Yeah, that's right. a good question. You'd have to, that's a good question. And the answer is, I believe you'd have to go to the first one, because if you had a complicated, if you had a log of a product like that, you'd have to be able to separate it into individual logs. And so you could only choose values of X that are going to be valid arguments for the individual logs. So we would have to discard the -2 here. Okay. So that one would go away, and we'd keep the 5. Mm-hmm. Because log functions don't allow that. If we look at, we already looked at the graphs of log functions, right? No, have we not? I don't know if we did. Yeah, there's an example, right? So this was the next step. So who am I? Name that log function. That's a base what log? Okay, look at the inputs and outputs. Well, your input would just be the X value, right? So every log, if I input 1, I get back 0, don't I? Because I think what that's saying, the log of base, who knows or cares, right? What's the only way that any base taken to some power is going to give you back 1 for an answer? 0, right? That's the 0 power property. Anything to the 0 power is equal, other than 0, is equal to 1, right? So you know that regardless of the base of the log, in fact, rather than a question mark, let's be a little better than that probably. Let's call it a B. The base B log of 1 has to be 0, because any base to the 0 is equal to 1, right? But look at this point right here. Look at this one. That's saying the base B log of 10 equals 1. So in other words, that's saying that B to the 1 equals 10. What must B be? 10, right? So this has to be, who am I? I am a base 10 log. Okay, but look at what a base 10 log looks like. This is the graph of a base 10 log function. It's asymptotic on the negative y-axis, but what are the allowable inputs then? Well, we can only input values greater than 0. It's undefined. You can't, log functions are undefined for negative input values. Okay, that makes sense? Okay, and okay, yeah, nothing more to say about that. Okay, so going back to this one then, does that now make sense why we can only pick values that are going to be allowable inputs, which would be values where I'm going to, the argument of the log function, the number that the log sees is going to be a positive input. Okay. All right. How about if we graph it? Let's graph it and just show this graphically. Okay, so we've got the log of x plus log of x minus 3 gives us that. Okay, well, look at that function. You can see here that of the two input values, like 5 and negative 2, negative 2 isn't going to work. If I define that as f of x, how about? F of x equals that log function. I want to know when is that equal to 1. Okay, well, I could just come down here and graph the function y equals 1, and there's the intersection. It occurs when x is 5. Okay, there is no solution when x equals negative 2, because look at the red graph. It's not even defined for x values of negative 2, right? That's why it can't be negative, yeah. Okay. Here, I'll include that. I'll include this. That might be helpful. I'll include that in the notes. How about? Yes? Okay, good question. Let's check it out. It should, right? It needs to. So let's turn that one off and let's create a new function. G of x equals log of x times x minus 3. And what's that doing? How come that's giving us two graphs? Yeah. Yeah. And that's so in the compressed version, look at the two solutions we get. We get negative 2 and positive 5. And I would argue that we have to discard the negative 2 because that's not a solution of the original expression, right? When you write those as a product, what's going on there when you write those as a product, x times x minus 3 is the same thing as x squared minus 3x, right? X squared is an even function though, right? It's invariant to the sign of the input. It's got even symmetry. And so you're introducing some extraneous solutions when you compress those into a single function. Okay. Yeah, that's kind of cool little study there, isn't it? Desmos is just awesome. Like the fact that you can go in and graph this stuff in Desmos, it just makes it so much easier to see what's going on. Did everybody get though why that green one was a little bit different? Okay. And if you could just make a simple logical argument there too, right? If this is the graph of the compressed version and this is the graph of the uncompressed version, the most restrictive has to be the one that you keep, right? Okay. All right. So who am I? That's a weird decimal. What is that decimal? You could figure it out, right? Because you know that this is some log function, right? So the input of the base B log of that weird number, 2.7182, blah, 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 is equal to 1. What is that number? That's E. Yeah, right? So that's saying B to the 1 equals E, so B must equal E, right? So that's a base E log. So I am a natural log. Okay.
How would you say E? Is it just like?
Say it again.
Well, how would you say E? Is it just E? Is there like
E?
some, like?
Yeah, just like pi is pi. Yep.
Oh.
Yeah, I'll show you guys later in the year. You know, not too distant future. I'll show you how to derive the value of E. You derive it with integral calculus. Okay. Who am I? Yeah, it's got to be base 2, doesn't it? Right? Because it's like saying 2 to what power, or b to the 1 is equal to 2, right? b to the 2 is equal to 4, right? So b must be 2. Everybody see that? Okay. Base 2 log. What's like? Let's just take that point right there, for example. So I just want to make sure. Like, if I take this guy, what's that saying? I'm inputting a 16 into my base b log, right? So the base b log of 16 is equal to 4 is like saying b to the 4th equals 16. Well, it's got to be 2 then, doesn't it? Okay. Who am I? Look at that. Tell me with that point right there. That one gives it away. It's got to be 4, doesn't it? Right? Make sense? Okay, because b to the 2 has to equal 16, right? Okay, so we've got you know how to, you've seen a bunch of practice problems. Now we move into the calculus of logs. So what if we want to come up with a new derivative here? We want to come up with the derivative of log u. So y is equal to log u. How could we derive this new derivative rule? We don't yet know. We're trying to show. Our goal here is to figure out what is the derivative with respect to x of log u, right? That's our goal. We want to be able to fill in the blanks here. What does that equal? Okay. What could I do?
Convert it to like exponent.
Yeah, we do know how to do exponential functions, don't we? We already know the rule for differentiating exponential functions. So let's turn this into an exponential function. Isn't that the same thing as saying that's a base? Remember, there's a base e there, right? And a log is an exponent. So e to the y equals u. Okay. Now I could just implicitly differentiate with respect to x, and I'm going to get my y prime popping out of that. How about that? Right. So what's that going to give me? If I differentiate with respect to x, on the left side, du dx is just u prime, right? Oops. Right, so I get u prime, and then the derivative of e to the y with respect to x, what's that going to be? What's the derivative of e to the hand? E to the hand, right? So the derivative of e to the y with respect to x is going to be e to the y times y prime by the chain rule. Everybody see that? Because you're differentiating with respect to x. The derivative of e to the hand is e to the hand times the derivative of hand. Derivative of y with respect to x is y prime. Okay, so I get that. I'm going to pause there. I'm going to make sure everybody's okay with that step. That's an important one. E is a constant, right? The derivative of e to the u. We know this derivative. We've done this one a lot, right? We know that the derivative with respect to x of e to the u is equal to e to the u prime, right? By the chain rule. Right? Okay, that's one of our derivative rules. Okay? So then I just solve for y prime. Okay, well we can do that. Well, what is, if I solve for y prime, I get y prime equals u prime over e to the y. But what was e to the y equal to? u. Yeah, look at that, right? Right? So we get out of this then u prime over u. I don't even need that step, do I? Because I've already defined e to the y as u. So there's my rule. The derivative with respect to x of log u is just u prime over u. We got a new one. Okay, so incidentally, sometimes we encapsulate the u in absolute values to ensure that we're inputting a positive value into log. Turns out that that has no impact on the calculus, right? The derivative of, in other words, the derivative of, I'll rewrite it up here. The derivative with respect to x of log of absolute value of u is still equal to u prime over u. Doesn't make any difference. Doesn't make any difference. Okay. Okay. And here's why. Because you get absolute values on the top and the bottom. Okay. And so when I look at those as piecewise functions, the negative part of the piecewise function would just cancel top and bottom. But we don't need to go into that. It's not important. Okay, we good? Okay, let's try this. Let's practice this a little bit then. So what about something like that then? If g of x is the natural log of x squared, then what's g prime of x? Derivative of log u equals u prime over u, right? Okay. So what's that going to give me? What's u prime? 2x, right? The derivative of x squared is 2x over x squared. Well, what's that equal to? I could simplify that. That's just 2 over x, isn't it? Right? Huh. Is there another route we could take to that one? Ah, yeah. We know we have a property of logs there. The log of x squared is equal to 2 log x, right? Okay, so we could just do that, and the derivative of 2 log x is 2 times the derivative of log x. What's the derivative of log x? 1 over x, right? Because in this case, u is just x, so u prime would just be the derivative of x, which is 1, right? So that's just giving us either way we go, we're going to get that. But the yellow way is a little bit easier, isn't it? Right? It's a little bit easier to take advantage of those properties of logs. Okay. Here's an example where it wouldn't even be close. And that one you might say, yeah, I guess it's easier. They're both pretty easy. But how about that one? Doing that the first way would be ridiculous, right? I mean, that would be a really ugly problem. If I'm just going to just power through that with the derivative of log u is u prime over u, yikes. U prime, I've got to take a derivative of a square root of a quotient divided by a square root of a quotient. That sound like fun? Not really, right? This is pretty simple though. If I expand that using properties of logs, way easier. What do I do with the 1/2 when I'm differentiating? Leave it out front. It's a constant, right? So the 1/2 stays out front. And then I just have to differentiate everything inside, but I've just got two terms. I'll just differentiate term by term. What am I going to get from the derivative of log of x plus 1? Well, that's just derivative of log u is u prime over u, right? So what do I get, Tori, what do I get from that derivative of log x plus 1 then? Yeah, 1 over x plus 1, right? Minus, what am I going to get from the derivative of log of x minus 1? Olivia, what's that going to be? Done. Boy, that was easy, right? Okay, so simplifying, those properties of logs are invaluable. They untie these arithmetic knots. I've got powers of quotients here. Man, by all means, you want to knock those a rung down the ladder, make them easier combinations, right? So the arithmetic becomes much, much easier. Okay, give me 1 to 5 on that. Does that make sense? Okay, you see the moral of that story. Take advantage of the properties of logs before you differentiate. Okay, try that one. Try that top one. Again, that'd be pretty nasty if I'm just gonna force u prime over u on that thing, because u's pretty ugly. So what do you think? What does that simplify to as a log function if I expand it?
Log 4 plus x squared
Okay,
minus log x.
minus log x. Everybody buy that? Now just think, again, I don't want to take, like, I could go through and do this the hard way, but why waste all that time? You guys can remember back what that was like, though. If I had to differentiate, u prime would be kind of tough. I've got a quotient rule involving a radical. Remember that stuff, right? Where you have to factor out the least common power, and it's a bit of a process, right? That's no big deal. Okay, so what's y prime? Let's take that first term. Maria, what's going to be the derivative of that first term? No big deal. Okay, Jonathan, what's the derivative of that second term? I'm going to get minus.
Minus 1 over.
There it is, right? And look, I could even cancel the 1/2 of the 2. That's no big deal, right? Okay. How about one like that? Oh, what did that do? Okay, is there a property of logs I could apply here? I mean, I could take a log of a power I could do something with, or a log of a product or a quotient, but log function, log of a log is not included in the prop. So I'm properties of logs, right? I'm kind of stuck with this the way it is, but that's probably okay. So what goes on top? What's u prime? What's u in this, by the way? Log x. Okay, so what's u prime then? 1 over x, right? Derivative of log x is 1 over x divided by u. So 1 over x divided by log x, that's the same thing as 1 over x log x, isn't it? Dividing by log x is the same as multiplying by 1 over log x. Okay? All right, good place to stop.